Welcome to the structural analysis class. So in this class, we will solve couple of problems. So initial first 6 lectures, we have discussed the basics of structural analysis, starting with free body diagram and then material properties. We discussed about different types of loads which will be involved in the structural analysis. Then we have discussed equilibrium of structures. We discussed how to idealize the original structure into analytical model. Then in the last class, we have discussed how to calculate indeterminacy of the structure and how to determine the stability of the structure, all these things. So in this class, we'll solve couple of problems. So our first problem one will discuss the how to do the load calculation and all. So the problem statement is the floor beam in the figure which is shown below is to support the 6 feet width of a lightweight plain concrete slab having a thickness of 4 inches. So you can imagine that. So this is the slab I am talking about. So it is a 6 feet total. So see, this is so this entire slab is resting on this beam. So this I section beam is there at the bottom. So this slab is resting on this beam, and the masonry structure is actually resting on this slab. So this is the entire structural system in this problem. So the length of the beam or the slab, actually it is a total 6 feet. That's what it is mentioned. So the width is actually 6 feet and the thickness is 4 inches. So this thickness I am talking about is 4 inches. The slab serves as the portion of the ceiling for which floor below. So basically this is a floor slab, and below that there is a floor. So when you have a floor, so we have plastering also in the slab. So that's what. Therefore, its bottom is coated with a plaster. Furthermore, a 8-inch high, this is 8-inch high, 12-inch thick, lightweight solid concrete block wall is directly over the top flange of the beam. Determine the loading of the beam measured per foot length of the beam. So our main objective is basically to analyze this beam, whatever is at the bottom. So in this problem, they asked how much load will be going to this beam. So that actually we have to calculate. So before analyzing this beam, we have to find it out how much load is acting on this beam. So in this problem, basically we have to find it out up to how much load is acting in this beam per meter or per feet width, per feet length, how much is the load. So let's start one by one. So we discussed what is dead load. So dead load is the self weight of the structural member. So here, what are the structural members or what are the loads coming into the beam? So if you see this slab load, whatever slab load is there, that is coming to this beam. Similarly, some plastering also may be there in the soil, in the slab. So that plastering load also come to this beam. And then you have this entire block. So this block, weight of this block also coming to this beam. So three types of loads are coming to this beam. One is this slab load, whatever load in the slab. Second one is the plastering, which is done on the slab, plastering load, and then this block, entire block's load. So these all three loads are coming to this beam at the bottom beam. I'm talking about this I section. So this beam. So we have to calculate individually how much load is coming to this beam. So let's first start with the concrete slab. So concrete slab, this is a concrete slab. How much load is coming from this beam? So how to calculate this? So we have to find it out. What is the density? We know the density of the concrete. So basically it is 25 kilonewton per meter cube is the density of concrete. But if you convert into that is pounds and feet, then it will be 109 something, 109 pound uh, uh, per feet cube. So you know the density already, density of the concrete or whatever may be the material. So here it is concrete. Now we have to find it out how much is the area of this slab. So the unit weight of concrete is basically 8 pound per feet inch, if it's square inch. So that already we know the what is the density of the concrete slab. Now what is the area of this concrete slab? So concrete slab total length is total 3 plus 3, 6. So that's why it is mentioned here 6 feet is the length. And how much is the thickness? The thickness is 4. That's why 4. So we multiplied density with a cross-sectional area, and you will get how much load is going on, how much weight of the slab that we calculated, 192 pound per feet. That much is the load of the slab going to this beam. Now next is the plaster ceiling. So ceiling has this plaster as I mentioned. So the normally the plaster's uh, density is 5 pound per feet square. So these values are actually constant. You will get it in the table. So we discussed in the second lecture loads. In that you will find all these values. What is the plastering? What is the density of plaster? What is the density of concrete slab? All these things. So 5 pound, and how much is the plastering length is 6. That's why it is 6. So we will get 30 pound per feet. Load is coming from plaster, and from concrete slab 192 pound per feet is coming. Now what about this block wall? So this block walls, so the density of the concrete I mentioned, it is 105 pound per feet cube. So this will be the density multiplied by the cross sectional area. So how much is the cross sectional area? So the total height here is 8 feet, and we are calculating unit. So and the width is how much? 12 inch. 12 inch means basically 1 feet. So that's what is the cross sectional area. So 105 is the density, and this is the height 8 feet, and the thickness is 12 inch. 12 inch equal to 1 feet. Just substitute this, you will get 804 pound per feet. So the total weight coming to this beam is, just add all these three, you will get the total how much. So it is 1062 pound per feet load is coming. So if you consider 1 feet length of this beam, then 1062 pound load is acting on this beam. So that's how you correctly calculate the dead load of the structure. So next, problem 2 will discuss about the whether the beam is determinant or indeterminate. So last class we have discussed how to calculate the indeterminacy of the beam. So what is the formula? If you remember, we have used a number of unknowns. Reaction force, we call it R. If R is equal to 3N, then we call it this beam is a, or this structure is a statically determinate structure. If R is greater than 3N, what is N? N is the how many parts are there in a building, in the structure. So if this condition is there, then the beam is actually, the structure is indeterminate structure. So this is our basic formula we derived last class how to do that. So now let's solve this first problem. So this is a structure which has basically two parts. You can understand this is a one part and this is another part connected through a pin joint. So total, now we'll calculate total how many forces, how many reactions are there in this structure. So first is, this is a roller support. So roller support, it is actually hinge support, which is this direction is a roller is there. So it can rotate, go in this direction. So vertical direction, the movement is allowed. So reaction you will get from here is this one, horizontal thrust as well as moment. So from this support you will get two reactions, and this joint is a pin joint. So each pin joint has two reactions, already you know, two direction. This is vertical reaction, horizontal reaction, and this is also a hinge support. So hinge support also has two reactions, so horizontal and vertical. So total how many reactions are there? So here two, in this joint two, in this joint also two, in this joint two. So two here and two here. So total 6. That's why R is mentioned 6. And total number of parts is, this is one part and this is another part. So N is equal to 2. So if you just substitute the formula, R is, you have 6, and then 3 into N is 2. So 6. So 6 equal to 6. So this beam is basically the statically determinant beam. You have to calculate first what is R and then what is N. N means number of parts. How many parts are there? So here two parts. Now in this beam, if you see in the second problem, this end is fixed end, and this end is also fixed end. So total how many reactions are there here? So fixed end means, you know, there is three reactions. So horizontal, vertical, and you have moment. So three. So here also you have three moment: horizontal, vertical, and moment. So 3, 3, 6, and you know these two are actually pin joint. So pin joint means it has two reactions: horizontal and vertical, horizontal and vertical, two reactions. So total how many now reactions? So here 3, in this joint 3, here in 2, and here 2. So 3, 3, 6, 8, 10. So R is equal to 10. That's what is mentioned here. And N means how many segments are there. So here how many? 1 segment, 2 segment, 3 segments. So N is equal to 3. So 3N will be 9, but reaction is 10. So in this case, actually R is greater than 3n. So this beam is actually indeterminate beam. So this is a statically indeterminate beam of first degree, because you will get reaction 10 minus 9. So you will get 1. 1 is the degree of indeterminacy of this beam. So now this is a problem 3 we'll discuss. So problem 3 here, it is similar to frame structure. So let's do it here quickly. So this is a fixed support. So fixed means you have 3 unknown. This is a hinge support. Hinge support you have 2 unknown, and then this is also fixed support. We have 3, and the here pin is connected. Pin joint means 2 over. So total how many? 3 plus 2 5, 3 8 to 10. So R is here now 10, and total how many are the sections? So this is one section, and this is entire is one body. So basically two part here. This is one part, part 1. So this is one part, and this entire structure, so this is monolithical one body. So this is part 2. So n is equal to 2. So now if you subtract, uh, so 3 into 2 is 6, and R is 10. So it is indeterminate because R is more with a fourth degree, because 10 minus 6 is fourth degree, strictly indeterminate structure, this one. Now let's compute this one. So here you can see this is a fixed portion which is actually connected through a beam. So this beam is also connected. So this portion is anyway fixed joint. You can see. So only one, so not fixed actually, it is rotating. So it is sliding. So sliding means it can slide in this direction. So you have only one degree of one reaction in this joint, because this is a tube type. So it can actually move in that direction. And here you have roller support, and this here is a fixed means 3, roller means 1, and here 1, and you have pin joint. So here one pin joint is there, and here also another pin joint. So pin joint means 2. So now total how many? 3 plus 2 5, 6 7 8 9. So total R is here 9. And total how many joints are there, how many parts are there? So this is one part, this is second part, and this is third part. So we have n also 3, so 9, R also 9, and total known reactions are also 3 into 3 9. So this is a statically determinate structure. So next problem is this one, whether to calculate this beam is stable or not. So if you see, if you calculate how many reactions are there, so this is a roller support. So roller support means only one vertical up. So here also vertically up, here also vertically up. So you have 3 unknown. So R equal to 3. And how many n? N is equal to 1, because it is single phase. So it is a statically determinate structure. But if you see all the reactions of this beam, all the reactions are actually vertically up. So all the forces are actually parallel to each other. So if you remember last class we have discussed concurrent forces. So all the and parallel forces. So all forces are here parallel. That's why this structure is not stable. Why? Because if you apply this side, any this horizontal load is applied, then this beam will simply rotate, simply slide to this direction. So no support will give resistance to the horizontal force. So that's why this beam will simply slide to this direction if we apply any inclined load. So this beam is not at all stable, because even all the all the reactions are actually parallel. Now let's see this structure. So this structure also, this is a roller support. So roller support means you have only one vertically up, and then pin means 2. So here 2, here also 2, and this is a hinge joint also 2, and here 1. Roller is 1. So 2, 2, 4, 5, 6, 7. So total you have now R is equal to 7. And how many parts? 1, 2, 3. 3 parts are there. So 3 into 3 is total 9. So now in this condition what happens? R is actually less than 3n, because R is 7, whereas 3n is 3 into 3, which is 9. So if you remember our last condition, that is if R is less than 3n, then the structure is unstable. So this structure also unstable. Yeah. So uh, here this is another problem. This is a beam is given to you, and UDL is also acting here. So this is a fixed end. So fixed end means you have 3 unknowns. So here you have 3 unknowns. So one is horizontal, vertical, and you have a moment. So three unknown reactions you have. So let's give some name A. So this vertical one is reaction A vertical, reaction A horizontal, and this is MA moment. So all these three components you have to find it out. That is our question. So how to do this? First you have equilibrium of equation. Summation of all vertical force is equal to 0. Summation of all horizontal force is equal to 0. Summation of all moment about is equal to 0. So these three equations we have. So now apply first summation of all vertical force, summation of all horizontal force equal to 0. So what are the horizontal forces acting? So here only RA is acting this side. So RAH, no other horizontal force. So RAH equal to 0. This is one part you calculated. Now next is summation of all vertical force equal to 0. So how many vertical forces are acting? So RAV is acting which is upward. So let's compute upward as a positive. So we'll consider upward as a positive. So RAV is password then positive. Then 160 is going downward. So 160 will be negative. So just erase it. I will just change it to 160 is negative. Then negative. This 15 kilonewton per meter is also downward. So negative. So 15. How much is the total load? 15 into 6 total, the entire length it is acting 6. This is equal to 0. So from here you will get RAV equal to 250 kilonewton over. So this is done, this is done. Now next we have to calculate what is the force of MA. What is the value of MA? So how to calculate? So MA will be calculated last equation, that is summation of all moment equal to 0 about the A. So what are the moments acting? So 400 is acting. So 400 is a clockwise. So let's consider clockwise is a positive. So 400 plus. Then UDL is acting. So this entire UDL, if we convert into point load, it will be 90 acting at the center. 90 how we got? 15 into 6. So total 90 is acting at the center. So we will have 90 into distance. So this distance. Force into distance is the moment. This distance is 4 plus 4 plus 3 is 11. This is also going to be clockwise direction, anti-clockwise direction. So anti-clockwise means it should be negative. So this is should be just a negative. Then minus one more force is acting, 160 is acting. So 160 into force into distance about A is 4. And then moment MA is acting also at this point. So moment A is acting. So this is also we considered anti-clockwise. So anti-clockwise means minus MA equal to 0. So from this equation you can easily compute what is the value of MA. So MA equal to 400 plus 90 into 11, that is 990, plus 160 into 4 is 640. So you just add it, you will get it total. This will be 1040 plus 990, you will get 2030. So that much is the moment. So all these three parameters we have computed now. RA is horizontal force is 0, that's what we computed here. And next RAV also we computed, vertical one, and moment also we computed. So all the reactions now we computed. So like that, using the equilibrium of equation, basically you have to find it out all the reactions. Thank you.